Bismillahirrahmanirrahim. Welcome to International Research Class. For this time, we will discuss about the one method to estimate the parameter of probability distribution function, namely Bayesian Markov chain Monte Carlo. So that why we give the title our discussion today, Bayesian Markov chain Monte Carlo or MCMC for estimate generalized extreme value or GEV distribution. The main issue in the Markov chain Monte Carlo is how to upgrade our posterior by using the formula prior multiplied by likelihood. In the case our prior don't have the information, so we can take the assumption our parameter is distributed by normal distribution. Okay, there is the one recent article that published in the one international journal, Mathematical Modeling of Engineering Problem in the 2021 with the title Power Bayesian Markov chain Monte Carlo for modeling extreme temperature in Sumatra Island using generalized extreme value and generalized logistic distribution. This recent article, there is two extreme distribution, namely generalized extreme value. Okay, you can check in the table 2 and generalized logistic. For the first time, we will discuss about how to estimate the parameter generalized extreme value using using Markov chain Monte Carlo. You can check here, there is the density function of GEP distribution. There is three parameters here, alpha, kappa, and C. Okay. In this recent article, there is the best algorithm for to estimate parameter using the MCMC. The algorithm used the X step. In the first step, initialize the chain theta 0 equal to pi 0, C0, kappa 0. This is the three parameter in GEV. The pi equal to logarithm natural alpha. So after we give the initialized value, so we try to produce the pi star or pi g equal to pi g minus 1 plus omega pi, where is omega pi distributes with normal with the parameter 0 and 4. Except pi g equal to pi star with the probability equal minimum 1a, whereas a equal to the posterior, of course the posterior GEV with the parameter pi star, C g minus 1 and kappa g minus 1 divide to posterior pi g minus 1, pi g minus 1, c g minus 1, and kappa g minus 1, and pi g equal to pi g minus 1 otherwise. After that, we try to take the C star. C star is the second parameter equal to Cg minus 1 plus omega C, whereas omega C distributes with the normal with parameter 0 and 0.3. And then we expect Cg equal to C star with the probability equal to minimum 1A. A is equal posterior C star and pi G kappa G minus 1 divide the posterior C G minus 1 pi G and kappa G minus 1 and C G equal to C G minus 1 otherwise. After that, we try to produce the sixth parameter of GEV, namely kappa, for the kappa star equal to kappa G minus 1 plus omega kappa, whereas omega kappa distributes with the normal with parameter 0 and 0.1, except kappa G equal to kappa star with probability equal to minimum 1A, where A equal to posterior kappa star given by G CG divide the posterior kappa G minus 1 given by G CG and kappa G equal to kappa G minus 1 otherwise. And then the last step, increase counter from G to G plus 1 and return to step 2. Okay, there is the X step in the algorithm for the MCMC method to estimate the parameter. So the problem is how to use the R or how to produce the good R programming to solve the MCMC problem using the X step in the algorithm. Okay, now we can check our programming. We stop there. So then we share our R programming. Okay. In the R programming, the first one, we must create the R programming to the likelihood. Likelihood Z for the our data, E is for the parameter, U for the pi, T for the C, then E for the kappa. And then we create the best programming for the likelihood. You can check here if the E equal to 0, so likelihood equal to T power minus 1 exponent min Zi minus U divide T minus exponent minus Zi minus U divide T. And then if the E and the else, we give the likelihood like this one. Okay. So we must definition Y become to Y is this one. Okay. After we are create or produce the best programming for the likelihood, so we try to produce the our programming to the MCMC based on the algorithm. Okay, you can check here. There is omega pi, nor R-num M with the parameter 0 and 4, and omega T, R-num M with the parameter 0 and 0.30, and omega E. So we try to make the best programming based on the algorithm like this one. This is the parameter U star or pi or C star equal to pi G minus 1 plus omega pi E. This is based on the algorithm. Then after that, we need the A. Okay, A is mean FF1 divided FF2, whereas FF1 is the posterior, FF1 is the posterior with the formula likelihood multiple by the our prior. Don't forget our prior distribution is normal distribution with parameter 0 and 1000. Okay, after that we can produce the parameter 2. So after we take 2, we must find the parameter T. The parameter T or C star equal to C J minus 1 plus omega C. Okay, so you produce the A. Remember to produce the A for Indonesia, A for the English. Okay. Okay, after that, we can produce the parameter kappa. Okay. So, Z for our data. So, we try to run this programming. For the first one, we need the data. Okay. Our data, ZZ data is mean we have the 21 data. This data the maximum temperature for the each year for the 12 station. Okay. So we just use only for the station one. Okay. So that's why we call the Z because Z for the data, Z is the ZZ column 2. Enter. So our data Z is only for the maximum temperature in the station 1. Okay, after we have the data, we run our program. Okay, we try run our program. From the F, this is the program for the likelihood. Okay, I will run our program. Okay, after that, we run our program, give the initial value or initialized chain for the I10 for the C1 and for the kappa 0, 0 minus 0 minus 0.1 and we burning until the 30,000. Okay, we run our program here. We run our program. Okay. And then we come to the console. So we wait for the program still process. Maybe yeah, okay. Our program is finished with the process. So we can check here if we try to text U is a parameter for the alpha. Of course, we must have the 30,000 the parameter U. Okay, we enter here. So this is the 30,000 for the U parameter or alpha parameter. And then if we try to type T is the for C parameter. If we enter here, we have 30,000 for the parameter C. And we type E for the kappa, and then we enter. We will take the 30,000 for the kappa. Okay, we have the 30,000 for the each parameter. Which means we have success to run our program. We're burning our parameter until 30,000. So to find the best one from the 30 parameter, we try to produce the trace plot and posterior density plot. Okay. We try to give the plot, transport, and the posterior density plot. Okay, you can check here. With the parameter 2, U, or the alpha, this is for the alpha, we have the good parameter for the safety parameter because our parameter is become convergent to the one value. To check the which one the value from the 30,000 value, we can check from the posterior density plot. Okay, you can check here for the maximum value in the posterior density plot. So we can take the value in the axis of x. Okay. The same case with the T or the C parameter. This is C parameter. You can check here. The C parameter is very nice. Very nice. Very nice. Our program here, we success to give the convergent from the 30,000 value to the C parameter. Okay. So C parameter you can check here between this one. Okay. Around 1. Okay. Because this is the maximum in the posterior density. So the value of the parameter around this one, around the 1. The same case with the kappa parameter, we success to generate 30,000 value for the kappa. The 30,000 is convergent, comes to the 1 value. And then we can check here, this is the maximum with the posterior density. This is 1 for the maximum value for the posterior density. And it's mean the kappa parameter between 0.5 and 1. So to try to find the fixed value from the 30,000, we can use the median of the parameter. Okay. For this one, we use the median U, a median U. Okay, we use the median U for the find the fixed value for the parameter alpha. We run. Okay, we try to median T to take the fixed value for the parameter C. We run here, and then we try to take the median E to take the fixed value for the parameter kappa. Okay, we come to our console. We check here. For the parameter U is 86.60. And for the our C parameter, 0.93. And our fixed parameter for the kappa parameter is 0.6, 0.56. Okay, we have success to create the R programming based on the algorithm in the research article. We success to run the program. We success to take the fixed value for the 3 parameter and GEP. Okay. For our student or for the researchers who's interested with this program, we try to open the slowly our program. You can check at your home. Okay, we can check slowly. Okay, our program, this one. The first time you must create the program for the likelihood value. After that, you are give the initialized change. Okay, and then you need the M equal to 30,000. It means we must burning this program until 30,000, and then you give the omega U, omega T, and omega E. So you try this R programming to the MCMC Bayesian. Okay, you can check here. This is for the find the parameter U or alpha or phi. This is for produce the parameter C, and then this one the produce the parameter kappa. Okay, you can check in your home. If you need discussion with the international research class, please contact me. We will discuss together. Okay. Rado Yendra with the international research class. See you again in the another program.